We went through this, right? Literally every test is a main number that we check if it's zero or not using a sampling distribution with method number 1, which is the confidence interval. Method number 2 is the critical value. So let's talk about that one. It's actually the same thing mathematically, but it's a slightly different way to look at it. So let's imagine 2 worlds, okay? Let's imagine world 0. World 0 is a world in which, your population, this is your population distribution, it's a world in which the main number in the population is 0, okay? Let's assume we live in a world in which it doesn't matter how much Instagram you use, you're always like poker face. You're always just like average happiness. You're just like with lots of Instagram, with no Instagram at all, same, nothing changes. Let's work with world 1 too. World 1 is a different world in which the population distribution has a certain value. I'm setting it to 4, but it could be literally any value that's not 0. I'm setting it to 4 as an example. And here, in this world, there's a 4-point difference in depression between Instagram and no Instagram users. So if you don't use Instagram, you're super happy. And if you use Instagram, you're fucking miserable, okay? This is a world in which the difference is huge, okay? The 2 worlds we're going to be working with, okay? These population distributions are referring to all the 2 billion users of Instagram, right? Nice. Reminder, again, now I'm going to be talking about the ideal sampling distribution, which is something we learned in the all distributions class. So go back to that for a recap if it's not super clear. But the ideal distribution is that, just a quick recap, is that distribution that we get by taking many samples from the population and building the distribution of how likely it is that we will find a sample of value X. It's the cousin of the derived sampling distribution, as we learned, right? The derived sampling distribution is a slightly poorer version of this, right? Okay, so we have our ideal sampling distribution. This is ideal sampling distribution. Let's say that we captured 25 samples from this population, okay? And these 25 samples, they varied from -1 to 1 difference in Instagram users, right? So sometimes you could see the users were slightly happier using Instagram, and sometimes they were slightly sadder using Instagram. And the difference is not clear. Sometimes it goes up, sometimes it goes down. But most of them, right, the most samples had a value of exactly 0 or values very close to 0, as we can see here in the difference between Instagram and no Instagram. Cool. So this is the ideal sampling distribution. Why? Because we had the opportunity to use many samples to shape this. Again, this is something that we can't really do in day-to-day life in statistics, right? In day-to-day statistics, we only have 1 sample. We have to use that shitty derived distribution, which is all right. But this is a very robust distribution. So we got that. And so there's some wiggle room for random error. What do I mean by that? Well, sometimes when you're gathering your sample, right? And these samples, when I mean that we had 25 samples, each sample had like 300 dudes, okay? So it's like 300 dudes here, 325 times. Nice. So but even though we did that, sometimes, when you're gathering a sample, you find 1 too many happy people or 1 too many sad people, right? Maybe there's people who are too depressed or people who are too happy, and they're going to be affecting our results. So we have to give some wiggle room for random error. Sometimes it's going to seem that there's more difference or less difference. So you might ask me, Izaki, how the fuck is it possible that we found a sample with difference 1 if we know that the value in the population is 0? Well, and that's exactly the thing that I'm telling you. So maybe you got a sample in which people were too depressed. And then it seems that the difference in depression of using Instagram is going to make you more depressed, right? 1, it's going up. Or it can be that you found people who are way too happy. -1 in your sample, in this sample, which is an exception, by the way, because it's very difficult to find people who are too happy, If people were too happy, then they're going to be like, oh, what's the difference? When they use Instagram, well, they become less depressed, right? It goes to -1, less depressed. But all in all, the average is 0, right? Because we know that this is the value, that if we were to go in the population and measure everyone's depression and add it all up and take the average of everybody, that would have been 0, right? So Instagram would have 0 effect on people's depression in this hypothetical world. Nice. So in this case, 95% of the samples have a main number between -1 and 1, okay? Right? So out of the 25 samples, probably around 20 or 22, 20 something had a main number between -1 and 1. Some samples had a value outside. That's not the point. Look, despite the wiggle room, we know everything coming from the population of world 0 is 0, okay? everything is coming from the population of world 0, right? We know everything's coming from there. It doesn't always have to be exactly 0 for us to know that this is coming from world 0. Now let's talk about world 1, right? World 1 has a population distribution with the main number 4. What does this mean? It means that the difference in depression when you use Instagram causes an increase in depression of 4, right? So if you had depression 0, in this world, you use Instagram for a month, now you have depression 4 out of 7, which is pretty absurd, okay? Now, let's say we do the same thing. Let's say we take 25 samples of 300 people in each sample, right? Then the main numbers for each of those samples is going to be ranging from 3 to 5. Some samples are going to have a main number of 3. Some samples are going to have a main number of 5. Same thing that we did for world 0. Now, there's some wiggle room, right? For random error. We know that the total average in the population is 4. And despite the wiggle room, we know that everything is coming from world 1. We know that for sure. Why? Because, well, maybe some people in your sample, some samples had, the sample here that had a main number 3. This sample specifically probably had 300 dudes who were not so prone to depression because they use Instagram and their depression jumped from 0 to 3, for example, right? Increased by 3. Those guys on 5 probably are more prone to depression in that sample. So this sample here that had the number 5, those 300 people probably were very prone to depression. But if you take an average sample of people who are prone and also not prone to depression, they sort of cancel each other out, and the number we have is 4, right? This is the most likely sample that we would find. So it doesn't have to be exactly 4 for us to know that this is coming from world 1, right? There's some room for error. Cool. So given all of these, we're just going to change this. We're going to come up with a new name. So for world 0, it's a world in which the null hypothesis is true, okay? And now we can say the word true because this is a hypothetical example. We never say the null hypothesis is true because we never know what the value in the population is. But in this example, we're Jesus Christ and God himself, and we know everything, okay? So in this world, the null hypothesis is true. So we're going to call this H0 distribution, right? Because it's the distribution in which the null hypothesis is true, okay? Same thing for the other one. This is world 1. It's a world in which the null hypothesis is not true, and we work with the alternative hypothesis, which is called H1. If you read H1, it's saying that the value is not equal to 0, and it's a world in which that null hypothesis, or that alternative hypothesis, H1, is true. That's why we're going to call it H1. You can read the hypothesis if you have any questions.